How about a little trigonometry review? So, ka, toa. That's probably how you remember them. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Kids love formulas, but it doesn't mean a thing to me without a diagram. So we have the hypotenuse and the side that's adjacent to the angle and the side that's opposite the angle. And if you like my labeled diagram, then you should use one too when you do your work. So let's make up a problem. We have a hypotenuse of 10 centimeters and an angle of 40 degrees. And what's really weird here is I'm even using units for a trig review. That's how much I like units. If I want to solve for the opposite side, I'll use sine because it has opposite, hypotenuse, and it's got the theta in there, all the things that I need. Make sure that calculator is in degrees mode, and you're going to get 6.43 centimeters. I'm including units in my answer as well. Now, to find the adjacent side, I'm going to use cosine because it has the adjacent side in that formula along with the hypotenuse. You might say, well, you could just use this number here and do tangent, but that uses a number that I've just calculated. And what if I did that wrong? Now I get that wrong. So I'm going back to the original information in the problem. And I get 7.66 centimeters. Now, before I go any further with my review, let's just ask ourselves, is this number reasonable? Kind of like when we do the labs and we ask ourselves, what's the estimate? Well, if this is 10 centimeters and that angle is 40 degrees, it's somewhere in the ballpark of being drawn roughly to scale. It maybe should be a little higher than that. It's somewhere around there. Then this side and this side look to be about those numbers. Now, which one would be the bigger one? If this angle is smaller than 45 degrees, this has to be longer than the opposite side. Hey, that seems to work. Could I check this using the Pythagorean theorem? Just square that, square this, add them together, square root, and you're going to get your 10 back. I mean, it's really, really close. So yeah, that's a great way of checking. Let's continue to check using the tangent formula. Let's plug in the opposite and adjacent side, and we'll solve for the angle. First, do you notice that there's a centimeters and centimeters both in these values? They're going to cancel out. That's the way trigonometry works. If I take the inverse tangent of a value, that value cannot have units. You should be able to run that on your calculator and you'll get 40 degrees. Now, it can always bother kids when we rotate a diagram a little bit. They lose their perspective. So let's work this one out here. If we say that this is the angle, now that's the adjacent side, that's the opposite side. Of course, the longest side opposite the right angle is the hypotenuse. And that's what all this trig stuff works with, is right angles. I'll use tangent to solve for theta. Now I'm really showing a lot of work, more work than anybody should really need to show. But just to let you know, if you have tangent and you want to get theta by itself, you have to do the inverse tangent of tangent. And this is the way you write it out, inverse tangent of tangent. That's going to leave you with theta on this side. But if you take the inverse tangent on this side, you have to take the inverse tangent on that side. And so that's writing it all out. Now I'm getting something like 57.9946 degrees. Well, that's too many digits. We don't need that many. We need to round off. So what do I see kids do? They say, oh, that's too many. We'll just round it off to 57.99. Okay, that was less than a half. You know, you can go down that far. But what if I wanted to round it off to 3 sig figs? Kids will still go like that. That's not legitimate. You can't do that. You can't just get rid of the 9. It would round up to 58.0 degrees. That's the way I'm going to write it. Hey, we don't even need trig to solve for the hypotenuse. We could use the adjacent side squared plus the opposite side squared, square rooted to get h. Okay, I get 9.43 centimeters. But what about some trigonometry to do that? Let's try sine and see if it works. Rearranging, substituting values, and I still get the same thing. I'd like to point out that I do have units here because I have them for the 8 centimeters. The sine of 58 degrees does not have units, but the units come from the 8 centimeters. I know when you think about trigonometry, you're thinking triangles, but really it's based on circles. If my radius sweeps out angle theta, I have a point at the end of the radius at the circle, which will have coordinate x, comma, y. Many times in physics, we deal with circles and circular motion, and this is often a very useful diagram. We can now think of the radius as a hypotenuse, and the formula becomes y equals r sine theta. Y is the opposite side. And the adjacent side, which would be x, that's equal to r cosine theta. This is really how I remember those formulas. Now watch this. I'm going to draw in a tangent line. Now you have to imagine the radius sweeping out the angle, starting from the positive x-axis going counterclockwise. And now imagine that radius being extended so it intersects the tangent line. What would be the length of that line segment? I'll call it y. It's opposite theta. Following the format previously shown, we'll say that r tan theta equals y. R is actually the adjacent side in this diagram. So it's really the same formula as opposite over adjacent equals tangent theta. Now this is why they call it tangent. You're finding the length of a tangent line. So far so good if we have right triangles. But somebody emailed me and said, what if we don't have a right triangle? Well, sometimes we can use the law of sines. I'm going to label my diagram like this. A, B, and C are the lengths of the sides, and we have theta and we have alpha, and I'll throw in gamma. It's pretty easy to remember. It's just the sine of one angle divided by the length of the opposite side is a ratio which is equal to the sine of another angle over its opposite side. And that is equal to the sine of the last angle divided by its opposite side. So it's a pretty easy formula to remember, and you only need to use 2 parts at a time. You don't use all 3 at once. Okay, for example, let's say we have 15 centimeters here for side B, and we have our angles labeled, and we need to find out what side A is and side C is. Well, we have to substitute some values into the equation. Take a look at that, see if it all lines up in your head, and then solve for A. I cross multiplied, I get 10.26 centimeters. How about solving for C? We need to include this part, which has the third angle in there. But I didn't give you the third angle. Can you figure it out? Yep, it's 130 degrees because all 3 have to add up to 180. So now we'll continue on with the formula. So now I've got sine of 130 degrees over C, and that's what we're looking for. It's going to be equal to this term or this term. I could plug the number in for A, or I could go back to the original term and now solve for C. Either way, I should get the same answer. I do that and I get 39.16 centimeters. Now, I suppose you could say, well, how do you know that's right? One thing you could do is actually draw this to scale with a protractor on a sheet of paper and measure your sides. We'll do that in a future activity. But right now, you should be able to do your trigonometry practice sheet that I sent you.